as a diagnostic tool. Okay, so um, this is like a prequel. This is the movie before the movie. So we're going to work on that. Now, what is ultrasound? Is we consider ultrasound any sound wave or with a frequency of around or larger than 20,000 kilohertz. 20,000 kilohertz is it's a cycle that is 20,000 per second. Now, ultrasound, it is, I mean, the sound can be infrasound or could be ultrasound. I mean, the elephant will hear infrasound, which is a really, really low frequency. But the ultrasound, because it's a really fast frequency, it can only travels on or on liquid. So the ultrasound, it's very, very good. Is used for dolphins, for example, is used for submarines, is used for sonars. And because of the ultrasound is used in 3 different ways. So you can be used for cleaning, for therapeutic effects, and for diagnosis. So if any one of you uses or wear frames, when you go with the glasses to the shop, they will put it in a machine. They're going to submerge that one in a machine, and the machine is going to vibrate, and it's going to be using ultrasound. Also, the ultrasound can be used as a therapeutic. So phaco, when we use phaco machines, we are using ultrasound power to destroy the crystalline lens. Now, when we use diagnosis ultrasound, it is used, it's a type of ultrasound that we use into a really low power. We're talking about microwatts. And it's the idea of this is that there is safe and you can use it as many times as you want. Now, as you remember before, now we combine the last two slides, because the ultrasound travels perfectly in a water media and it has a really low power and it doesn't damage anything because it doesn't create heat, it can be used on the eye. The eye is the perfect it's a perfect environment for the use of ultrasound. Now, to create or to form an ultrasound device, you need a piezoelectric. It's an element that vibrates, and when it causes vibrations, it creates those waves, and those waves are electronically amplified and analyzed to create an image. So the piezoelectric, it's capable to turn electricity into sound waves, and this is exactly what it does and how it works. So a regular transducer, and pretty much any single transducer in the world, it will look like that. It's going to have a backing material, it's going to have the crystal. Can you see my mouse? So the crystal is here, and that is what vibrates. So when you see a probe that is very expensive, it's usually because of this crystal, because it's attached to this area by really, really tiny filaments. So traditional ultrasounds they look like that. They will have a shaft, is going to have a movable piece. This is for the UBM, or they're going to be different forms of probes. Now, these devices are handheld, and the user will position it in different ways into the eye. So if we want to compare, do a quick comparison between the inside and what we do and the regular ultrasound, this is a typical ultrasound. that it has this clear scan bag that you can place on the eye, or with the same probe, you're going to place an eye cup and fill it with saline water. It's almost like a torture to extract information from a rebel person. Um, and the way that we do it different ways. So instead of the patient being laid down and the water comes to the patient, or the saline comes to the patient, we're going to lay down the patient on here facing down, and leaning down, and all this area, which is the eye seal, it's filled with BSS and has a membrane that protects from the probe. So this tiny probe lives inside of the unit, and this membrane, it's encapsulated in this device, which is called the eye seal. Now, the most popular frequencies in ultrasound are 10 megahertz for A scan. That means this is a linear ultrasound that is measured basically to use basically to measure the distance. So when you implant cataracts, or where you have to calculate the power of the lens corresponding to the size of the eye, we use this device. It's called the 10 megahertz A. Then there are a series of different ones. You have 10 for B, 8 for diagnostic. There is a complete array of ultrasounds. When we talk about UBM, the most advanced one, and our device, it's very similar to that. And I will explain it later why it's a difference, and why and where is the difference between us and the rest. So going into the types of ultrasounds, the A scan is just a linear one, and this A is called for amplitude. So the A means amplitude. This transducer is stationary; it doesn't move, so it just goes one. Sorry, I lost. Okay, good. It just goes in one direction. I, and please, gentlemen and ladies, excuse my analogy, but I say, and I always have, I produce the analogy that the ultrasound, it's a female, because females are much better than men talking and listening at the same time. Men only talk and we never listen. So that's a fact. Sabrina agree with me. So maybe the rest of the men don't, but if I have Sabrina, I'm okay. So in in this case, the ultrasound piezoelectric probe will emit some sort of information, is going to emit the sound, but at the same time is listening. So every time a ray or a wave, a sound wave, will go and hit something, it will come back and tells, I found something, but it will continue. Every time that hits something, there is a part of that sound wave that is lost. So it loses a little bit of strength, but it comes back and tells you, I found something, I found something. And these one, two, three, these areas are called gates. And we measure that in time. So we know that the ultrasound is traveling and is measuring time. So we know that we hit the first gate in 1 second and the second gate in 1.1 second. And we know, because of the speed of the wave of the sound wave, we know what's the distance between one and the other one. So without going too much details, when you do a biometry scan, you're going to find different gates in the eye. You're going to find the cornea. So the cornea always will produce two lines. And this is important because when we use the R scan, the inside 100, you're going to see those interfaces really well. The second interface we see is the anterior capsule of the crystalline lens. The second one is the posterior capsule of the crystalline lens. And then we go retina and sclera. So this is what we normally the ultrasound travels in the eye at different speed. This is not so important for us because there is, if we found an eye with silicon inside of the anterior anterior segment, we have a problem. Well, actually, that patient has a problem because that doesn't happen. So the silicon will be always in the back, in the posterior segment. Now, what's B scan? And this is important because this is what we are working on. B scan, B is for brightness. I mean, if it's the whiter it is, the more solid the structure is. The darker it is, there is either nothing or there is blood or there is, I mean, it's different. So we measure B, we measure the B scan, the brightness, with a probe that is going to be moving. So the probe is, you remember those fans that will move from right to left and they keep moving all the time? This is how the probes move. They're going to be moving from one side to the other of the eye. And this is what they do. They're going to move from one side to another. So the more dense the gate is, the brighter will be. If the material inside is not so dense, it's going to be less white. And if there is no material, it's going to be black. So in another ways, so the strong echo will be white, really, really white, and a echo that is not so strong, it could be fluid. So in this case, you're going to see that this is one line, and then you're going to have a lot of lines to make this image. And this is how we achieve, this is how we take the images. This is a posterior segment ultrasound. It's easier to explain it like that so you can see it. That is a hyaloid um, uh, um, it's a steroid. I forgot the name. Anyway, now the grayscale will go from really, really white to black, and it is 256 different grayscales. So this is going to give us an array of colors. White, there is something. Black, there is nothing. And that's how we measure. Be careful with that, because sometimes black means that there is blood. So it's not only that thing. So as a summary, when we talk about a scan, and this is important for you guys when you go and talk to a doctor and the doctor asks you, do you do A scans or do you do B scans? When we're talking about an A scans for biometry, and we do not do A scans. We only do B scans. And when we talk about B scans, there are two B scans, the anterior and the posterior, and we only do the anterior part. So the one scan is one direction, it's only one line. The B scan, it moves a lot of lines to produce a whole image. There are some concepts that if the doctor that you're talking to, it's very, very smart, they're going to know these things. The inside have all of these concepts and all of these embedded in the software, but we don't, you cannot necessarily play with them unless you go into an advanced mode. Now, the amplitude, it is the maximal deviation that the wave, that the sound wave is going to move. So A higher amplitude is going to give you a big echo. Big echo reflection means that there is something dense in the eye, and a low amplitude reflection is going to give you a really strong, a really low or weak echo. That means that there is something there that is not so clear. That means something could be a piece of brick or a IOL or a vessel or the sclera wall. And another thing could be a tissue or a blood or a something softer. Okay. Now, when we test the unit and when we remember that I said the guy speaking, and that's as we use speakers on our phones in our cars, the ultrasound also has this volume, and you can speak really, really loud, soft, and that's the gain. The gain is the volume that we transmit that ultrasound waves into the eye, and it's called gain. In regular and standard ultrasounds, the operator will have access to a knob, and they're going to move it up and down depending on the tissue they're looking at. Our ultrasound, the Inside 100, it automatically is set for the best image possible, and we can modify that one post image. Now, the wavelengths, it's another concept that is important because the wavelengths of the ultrasound depend on the penetration and the resolution of that. So when you're talking about the wavelengths, is the distance between crest and crest, and this is important to measure because the wavelengths will give you the frequency. A high frequency is going to have a wavelength shorter, and a low frequency is going to have a longer wavelength. So it's going to be, it works a little bit different. It's counterintuitive. So a high frequency ultrasound is going to have a much um, shorter penetration, where a low frequency is going to have a long penetration. We are working with one of the highest frequencies in the market. We work with 50 megahertz. The only frequency that is higher than that was a prototype ultrasound produced by a company called iScience, that it was 80 megahertz, and that's not longer sellable at the moment. So 50 megahertz is the ideal wavelengths to evaluate anterior segment. Now, the higher the frequency, as I said before, the higher the frequency, the more resolution, but the less penetration. And the lower the frequency, the lower penetration, and the deeper, sorry, lower resolution, deeper penetration, lower resolution. So it's sorry, this is like a tongue teaser. So when you have a 40 megahertz, when this number is high, the penetration is short and the resolution is beautiful. When you have a long or a low resolution, a low frequency, you have a long penetration with a smaller resolution. Think in megapixels. Bigger number, more megapixels. Small number, small megapixels. And that's a way to relate to that. Now, I'm going to scan off this because this is more in terms of how we use this. But this is B-scan. Okay, you need to understand the difference between a B-scan posterior and a B-scan anterior. This is what we're looking for. We're looking for an image that allows us to see the anterior segment of the eye. We cannot reach this. And the reason we cannot reach this is because we have a too high resolution. We cannot go that deep. So we're working on 50. So of all the frequencies used in the anterior segment, you will find 20, 40, 50, and 80. We are 50, and that's the most popular and the best frequency in the market. On the posterior one, just for your information, you have 10, 12, 10, 15, 10, 12, 15, and 20. Those are in the back of the eye. But again, we do not do the back of the eye. Think of anterior segment, 50 megahertz. So the resolution will be dictated by the high frequency. So the higher the frequency, the better the resolution.
You take a break. I have a question, Rick. So up the page. What's the frequency for this equipment?
The frequency for the inside?
Yeah, inside 100. What's the?
No, the inside 100 is 50.
50.
Yes, 50.
Oh.
It's not 100.
Is it use 30? You know, when we take the testing in 50, we can't pass the all testings. So we
okay. Now we go
it in 30, yes, and all the testing are passed.
Yeah. Okay. So we that's sort of information that you don't give to your salespeople because things get confused. Now, every single instrument, every single manufacturer is going to produce a piezoelectric or a probe that they will nominate it as 50, as 40, or as 20. So if you see Quantel, for example, Quantel is reading, and I'm going to quote here, give me 1 second because I have it in my phone that they sent it to me. Quantel is reading between 30 and 35. That's the Quantel 50. And that comes from a doctor friend of mine that is a Quantel speaker. And he was in Quantel. So Quantel will read, Quantel 50 reads between 30 and 35. Helix.
It's 35.
Helix,
no, not only 30, 35. It includes, it covers different frequency from 20 to 60.
Yes.
But
yeah, yes. But what I'm saying is I'm comparing only the 50 megahertz. Quantel 50 megahertz, when you do the test, it will read between 30 and 35. And yet it is considered 50 because of the penetration and the resolution that provides. When you see the Helix, which is out of the market at the moment, but the iCube that was 40, I think that I was reading around 32. And because I don't like to lie, I'll give it to you in a second. Where is the chat here? I don't have it, but anyway, but I sent it recently to the team, and this is it's also reading around 30. So the LX1 reads its nominal 40. That's what it says in the brand, but it only reads at 30. So what I'm trying to say here is that every single device, it's producing a probe that is lower than the nominal figure. So I'll give you an example. So it's when you buy a car, the car that you buy says that when you see the speedometer, the speedo, it will say that you can reach 300 kilometers an hour. But when you in reality you test that car, you can probably go to 220. So, but
But
it's
when I drive it at 300, I can drive it. So
yes,
that
of
means
course.
yes,
But
that means
this is
when we
every
test
company
at
does the same.
on the 50 millihertz, and it have to to pass all testing. Now we can't. That's a problem.
The
Ah,
NMPA material did go in. The paperwork calls 50, but when you look at the spec sheet, it speaks to the 30 megahertz, 30 to 50. So all of the specification and all of the reports that were submitted to the NMPA did indeed specify the range. So even though we claim it says a 50 megahertz probe, all the spec sheets identified that it was between 30 to 50.
Yes.
So we're okay. That should not be a problem at all, Sabrina.
Yes, that's not a problem. I believe that, but it's a
Okay.
problem for the AMPA applications. Okay, it's another topic. Okay, let's
correct, correct.
training.
So
Yeah. Okay, thank you.
that topic, that is a very dangerous trap, because every single company does exactly the same. Every company will produce a device that is not necessarily giving you the frequency that they're claiming.
Yeah.
But what happens is that in certain occasions and certain specific eyes, the maximum frequency achieved will be 50. So you have peaks of 50, but the general evaluation will be around 30, 35. And that's normal. That's okay.
So, Rick, this is Roger. So there's something we need to be clear. We received the feedback from AMPA. They ask specifically about frequency, whether we should claim 50 or 40 or 35. So if we claim 50, we have to pass the test at 50 megahertz frequency, right? So the problem is we send the device to the testing center, but when we set the frequency 50 megahertz, there's nothing can pass actually. So we cannot pass all the tests, and so the only thing we can pass is when we set the frequency 35 megahertz. So the MP will come back to us and said, okay, should you claim 50 or should you claim 35? From a marketing perspective, the higher frequency, the better. The doctor, clinician believe that, right? But now we have to answer the question from AMP. How can we answer the question? How can we explain to them, right? If we do the 50 megahertz test, we won't be able to pass, right? Pass the requirements. But if we don't do it, AMP won't be convinced. So what we
Roger,
should
did they? So all of that has been submitted. Has the NMPA come back and asked that? And
yeah.
has Eric provided an answer?
Oh no, not yet. No.
We are waiting for that.
Okay, thank you.
Okay.
So that's the
Now,
question from MPA. So I think this could be question for Rick. I think.
I would like to know. I would like to know, how did the other devices pass the test?
They did.
Because
They did.
Exactly.
We don't know how they did, but they did.
well,
Yeah.
I'm telling you, I did an ultrasound training in Shibo many years ago, and it was with the iCube, and I know the iCube doesn't reach 40, and yet they commercialize it for 40. So I have the test for the iCube, and the iCube was um, um, sold and tested by the NMPA, and in reality, they had here. Okay, I found the test. Give me 1 second. I'm opening it here. So just to give you an example here, Alex reads at Alex that says it's 40, they read at 29.3, and the NMPA already approved it, and it's been sold there for many, many years. This is a problem, and this is basically a discussion that we need to have separate from this audience with Eric and with Morris and Barry, because I'm not going to be able to fix it. I can defend our position in terms of the other devices also produce a lower one. Every single other ultrasound in the world is not reaching 50. And if you want to challenge an NMPA, said, I'm going to bring you buy a Quantel and you give it to them and said, measure it. Does it measure 50? And they're going to tell you no, but you let them go. So somebody make money there, and we don't know how, or we do know how. So I don't know, Roger San. I don't know.
Yeah, Rick, I think we should move on from here. Keep going with your training.
Yeah.
And we can continue to review this between Eric, Andy, and Roger, and Sabrina and the NMPA.
Okay. Yes.
Okay. So this is like when you get
Sorry.
out of yeah. I wasn't prepared for that question. So okay. There's a few factors that will affect the quality of a scan when you do ultrasound. And one of the most common ones is the angle of incidence. When you have a perfect perpendicular image, the peak is going to be much better, because the sound will bounce back, because it has to be 90 degrees, bounce back perfectly and give you a really good image. But if the angle of incidence is not great, it's a little bit in angle, that angle of incidence is going to give you a different image. The main difference with the Insight 100 is that our probe is resting in a plate, and this plate will move back and forward, being always perpendicular to all the areas of the cornea and the eye. And that way we assure always perfect angle of incidence. And this is something that no other equipment will give you. Another thing that affects the result of the image is the texture and interface. So a cornea that has some sort of problems, or an iris that is not flat, so it's going to give you a different light profile. So for that reason, the iris, it's always less dense than, for example, the sclera. Sclera is a more uniform structure. Every single transducer has an area of focus, and this is very important, because on the inside, and I don't have a picture here, but on the inside, you're going to have a red line. That red line is going to be the area of focus. This area of focus is where the best image, best resolution you're going to get. When you are evaluating an eye for ICLs, you need to place as close as possible the iris plane close to that red line. Because if you don't do that, the image will not be at its best position. So every single transducer will have a focus zone, and this focus zone is the best resolution. It is indicated in the screen by a red line when you take the image. Keep in mind that the further you go, the weaker the image it gets. In our case, it doesn't affect much because we're working on the anterior segment, but that is a concept that some doctors will ask you, what is the attenuation? Anyhow, the attenuation is 1 decibel per millimeter, if somebody wants to ask in terms of numbers. The gain, which is called the TGC, the time gain control, this is a feature of many ultrasounds. Ours, it's already set as automatic, but because remember that I told you that we are basically measuring in time. What it does is that we present the image as the image was always take with no time. I mean, we give you the best image at time 0. That means if the sound wave touches the cornea at 1 second and touches the crystalline at 1.1 and then touches the back of the crystalline at 1.2, we're going to see the image when each area is being touched by the impact by the sound wave. So you get the best image all the time, not the time gain image. Another thing to consider in order to produce a good image is the artifacts. Anything that is there in the middle, even a piece of metal or piece of plastic left in the eye seal. We have Cheng here, and he's going to be, or Meiko, I believe is going to be building our eye seals. If Meiko decides to leave a piece of plastic in that membrane is going to produce an artifact. That artifact is going to produce a shadow, and that shadow is going to cast a weird image inside of the eye. So we always need to find out what is real and what is not. So for example, here it looks like an orbital tumor, but in reality it's because there is an ICL and a lens drop here, and is damaging that. So you can see here that there are shadows, and when you see that, it's because there is not enough gel. In our case, that's another beautiful advantage. We don't need gel. We submerge the eye into a balanced salt solution and produce really good images with no gel. I'm going to go a little bit faster here, but our worst enemy is, or the biggest competitor is the OCT. The OCT, it's a great technology, but the OCT cannot read in different areas. So if you see the OCT here, it's great, but it doesn't give you any information behind the iris, in the ciliary body, in the zonules, or what's happening here in the crystalline lens. So the OCT is great for a front picture, but it doesn't show anything in the back. We show everything. We will show this area and that area completely. So it is a much better one. And I'm a big fan of OCTs. I sold OCT for many years. I think it's a breakthrough what they do, and it's fantastic to evaluate the retina like that. But when you want to evaluate a structure that is behind the sclera, the OCT doesn't work at all. So remember that if the ultrasound will not travel through air, you need to have a good contact, and that's why we fill the eye seal with balanced salt, and we produce a beautiful image. Another rule: the probe has always to be perpendicular. That is not our problem, because the Insight 100 will always produce a perpendicular image. This is the beautiful of our machine, is it's not tech dependent. Sabrina can take the image, Roger can take the image, my daughter can take the image, and my daughter's friend that doesn't know anything about medicine can take the image, and all image will be pretty much the same, providing that the patient is well positioned. There is always echoes being produced, and those echoes are, the wider the echo, the more strong material or more strong surface or tissue is. That's called echogenetics. So the echogenetics of a hard tissue will be really, really wide, and the echogenicity of a blood is going to be pretty much black. And the best image is always obtained by positioning the area that you want to analyze in the focal area, in the red line of the inside 100. So as a summary, our device, it's an anterior segment imaging device that we obtain using ultrasound. We use something that is called very high frequency ultrasound. The difference between our device and the regular UBM is to a VHS for those ones that they are a little bit older, and a DVD or a 4K image. You get more information, more frames per second, but it's the quality of the frames are also important. Our device, it's automatic, it's controlled by robotic, it is reliable, repeatable, and it's not technical dependent. We can do applications on corneal-based surgery, phakic IOLs. We have a dedicated STAR ICL, and we probably will have other phakic IOLs very soon, just to have there. We can do some applications for cataracts, especially post-cataracts, to see where the lenses are, if the lenses are tilted, if the lenses are not tilted, what's happening with the capsule. And we are working at the moment very hard to bring some innovative glaucoma applications. So I don't know. Do you have any questions, or how did it go? I'm going to put back my camera.
Rick, I've got a question for you.
There you go.
You showed the A-scan images, or what our A-scan looks like in terms of the sound waves, and we measure peak to peak.
Mm-hmm.
When comparing an ultrasound signal to an OCT light wave, what I've done in sales is I've mentioned why our images are so clear and crisp and go through tissue. We measure peak to peak. In a light wave, it's a rounded top. There's not a sharp point to measure to get precision for measurements in a light wave. Have you heard that discussion before?
No, I haven't. The OCTs works with a reference mirror, and OCTs OCTs has around 3 to 5 microns resolution in the retina. Problem with the OCTs is they lose focus when they are in the anterior segment because they're optimized from the back of the eye, and that's pretty much what's happened there. But I haven't get into much details on how do they measure it, because they are measuring with a reference mirror.
Yeah.
That they compare the light going in and then against a reference mirror, and then they so it's a little bit more complex than the ultrasound. The ultrasound has a single point of reference where the if the mirror is different, it might have to
But
work a
again,
little bit. I mean,
it's also because the light waves are not peak to peak. It's more of a wave. Okay. And so if you were to show one of your first slides there where you showed how we measured peak to peak, the other images showed kind of a sinusoidal wave, and they're rounded peaks. They're not sharp peaks. Okay, there, like there. So if you were to look at, it's a rounded. So where's the very sharp peak of that? In a light wave, it's rounded on top. It's hard to find that top point. In the ultrasound, they're very sharp peaks. And you showed that in a previous, like see how sharp those peaks are? Yes.
So
very sharp
this
peaks.
This is 1A scan, and you can measure where the peak is. So you can measure,
right.
And if it's this, for example, this is highly exposed. This is perfectly, I mean, the volume here, the gain is too high, but this is normal because you have high gain at the beginning and then attenuates because of usually a cataract. When you see a difference between these two, you have a cataract already. But yeah, this is diagnostic, and you can measure here like nothing else. You can measure a tumor or something. Yeah, that's you have an incredible resolution here, and we can do the same.
Yeah. So that's my point. My point was simply our measurement from peak to peak is so very precise, as opposed to taking a measurement from a light signal bouncing off of a mirror. It's a rounded top, so it's not as accurate as ours. It's just one of the differences.
There you go. Okay.
So, Rick, thank you very much for such nice talk. I think it's give us very basic information about ultrasound. I don't think any one of us really understand before you give us talk. So, my question for you is, when we talk to physicians, right, we compare quintil, they have the same frequency like 50 megahertz. So how can we say, when a physician asks us why you think your image is better than theirs, the image quality is better than theirs? So, we have to have some reason fundamentally, I think, to explain to the physicians, doctors, right?
The first thing, and I will say this respectfully, I don't think our image is better than them. I'm absolutely sure that our image is better than theirs. And there is the big difference is the control, the robotic control of the system. When you have a unit that you depend on the technician to maintain a perfect angle of incidence and a perfect location, that doesn't happen.
The ultrasound tip moves closer to the subject matter and farther away from it when it's handheld. Our tip stays rock steady. So the resolution is better.
So when you do ultrasound, imagine that this is a probe. The probe might be hitting the area of evaluation at different angles. And when you hit in different angles, you will have different outcomes. When you have our device, it's robotically controlled. The reason that is called arc scan, it's because we scan in an arc. So our device sits in an arc and then moves based on an arc. The closest one would be a Quantel linear scan, which is linear all the time. But I don't know if you can see if you can see me, but if this is the tissue, I mean, if this is the tissue and I have a linear one, I'm not perpendicular to the cornea. If I'm if I'm here, I'm always perpendicular. but the eye in general is not flat. The eye is curved. So the crystalline lens, it's curved. The iris, it's a little bit curved. It's all, let's say that there is a little bit of curve. Now, when you do this position, which is, let's say that the linear one is the way to go, and this is the area. This is the area that I'm evaluating here. Okay, and I'm moving here linearly. But if I hold the probe like that, I'm off. I'm off. I'm not in. I'm not in perpendicular. If I'm moving like that, so with our device, we control the hand of the person, because it's not a person, it's a robot. So this is a perfect. Is you will always have the best technician holding the probe all the time. With the device, with the other devices, you may have, you will have Robert, and then you will have Barry, and then you will have Rick. You will have different technicians, and all of us, as good as we are, we're going to be holding the probe a little bit different. With this is a perfect machine. This is like a military parade that everybody will march at the same pace, and they move the arms and they move the legs at the same pace. And this is what we achieve with the inside. We have synchrony, we have repeatability, and it's control. So if the doctor says, oh, why do you think the image is better than the Quantel? Well, first, I don't think, I'm sure. And second, can you guarantee that your technicians will do the same scan over and over and over again? They can't. They can, and we prove it. We prove it. If you give me 1 second.
Yeah.
If
So
you give me
Roger,
one
some of these
second.
diseases, say glaucoma, it's a longitudinal disease, right? So the patient comes back and comes back. And so oftentimes in a clinic, it'll be a different operator using a UBM when that patient comes back, or they're going to go to a different clinic. It doesn't matter any instrument in the world, our image is always going to be the same every visit.
So in this case, we did cases, okay, and we measured the repeatability on the use of different units. And you can see that with the iCube, it's a 0.25 millimeter. So you have a quarter of a millimeter all the time wrong. And in the Sulcus, 41 microns. That's a lot. Then same with everyone's. When you see the inside 100, we measure over and over again, and our biggest error would be 12 microns. I mean, that will not change the course of the direction. But if you see 51, if you see 36, or any of these ones, that is a size. That is one size on ICL. And when you have one size in ICL, you can have a pupillary block. You can have an oversized lens, or you can have an undersized lens, and you're going to have a problem, especially for the oversized. That's where the problem is when we're talking about basically hyperopic lens. I know the hyperopic lenses are not famous in China. We mainly have myopics, but we do have a high incidence of angle closure glaucoma in China. And if we choose the wrong ICL and we induce more angle closure, that's it. That patient will have a problem. And
I
the
think
doctor may lose their license.
yeah, I think those data, this table is good material for us to talk about for the physician, I think. And yeah,
I'm sure of that. And then when you see, I mean, I know this was made a little bit with a bad marketing, with a bad with a little bit of evil eye, but the image created by Inside 100 looks like a primitive OCT. it is so good that people will think, nobody will think that this is an ultrasound. I mean, this is probably the worst image I've seen from an iCube, and this is a really bad image from a ViewMax. But we see, if I show you what is a really good image for an iCube, and I put it next to it, here it is. So this one, it's a really good image for an ultrasound. Sorry?
That's from IQ?
This is the iCube, okay? Look at it. It's not bad, but when you compare it against this,
Still not look good.
I know that, but people don't know better.
Mm.
When you put that next to this,
You see the difference.
There is nothing to compare it. This is driving a plane and the other one is driving a kite. I mean, it's just two different things. Okay? So this is what you're looking for. No ultrasound, nobody will have so steady hands that you can see this that perfect. And I've been scanning ICLs with UBM for a long time. I never got any image similar to that. Never, ever.
Mm.
So, and when you see problems like an oversized lens, you don't get that. You don't get this information here. You don't see where the fluid plates are. What you see from and if I mean, I can, when I talk about this one, I will put photos of images that I have before from oversized lenses. You never see the difference. I mean, you will never be able to achieve an image with any handheld ultrasound that the ones you can get through here. It's almost impossible. It doesn't matter how good you are, you will not be able to do it, because it's that arc that you're moving. Now, and I'm sorry to be now a little bit of a typical teacher. If you remember that I said that the ultrasound will give you peaks depending on the gates, here it is your first peak, this is your second peak, and then it will give you a peak on every structure. Now, because there's a lot of scans happening here, you're going to have a series of a lot of A scans that makes a B scan.
And that's 2,048 per image scans. 2,048
lines.
Yes.
There you go. Okay, so let me see what else we have here. Oh, again, so this is an OCT image. See, we were talking about why do I need an OCT and why do I need an R scan? Well, here it is, your OCT. This is like the patient has no lens. I mean, there is nothing here. The patient has no ciliary body. They have no sulcus, no nothing. How's this patient alive? We don't know. And then you don't know where you're measuring. But when you see that, you can see the difference. Now, if the doctor says, but the cornea looks much better, I said, are you going to put the ICL in the cornea or behind the iris? Because if the doctor wants to put a contact lens there, that's fine. They don't need an OCT or an Inside 100. But if they're talking about a phakic IOL, you need to see what's happening behind the iris, which with an OCT you cannot.
So sometimes we really get very clear image of cornea. Sometimes we don't. What's the reason?
Do you remember that I said about the red line, the focus line?
Mm-hmm.
When the focus line is towards the back, we are focused on this area. This is where we need to focus. These two clear lines that you can see here, it's telling you that we were perpendicular. So
Correct.
this is a great image because this is giving you perpendicularity. And then you know you're fine. An image without those two things is not a good image. But the focus of this image is here. And this is where we want to have focus. Having the cornea or not having the cornea when you're implanting an ICL is totally irrelevant. This is like bringing your mother-in-law when you want to eat a cake. It's irrelevant because she will not let you. So it's having the cornea, it's not important. If we want to have a cornea image, we're going to move the focal area to the cornea plane, and we're going to have a really good image on the cornea. And that is what we do when we're analyzing the keratoconus. So when we evaluate the keratoconus, give me 1 second here.
So basically, you can choose the focal area to
Yes.
do to do the image. Actually, if you want to focus on the lens, you can do the lens, and you focus on the anterior chamber, you can do anterior chamber
Yes.
or iris or
Yes.
cornea.
You have a limit. So that is
And each
called
of the
Z.
scans, we have automatic scans. Those scans are set up so that the focal plane is set. So a cornea image will be, the focal plane will be set to the cornea, anterior segment, more at the iris plane, and for the ICL off the anterior capsule.
Okay.
We automatically set the depth, but then you can go manual and you can change it if you wish.
Oh, that's something good to know.
Yes.
I'm looking to see if I can find a image that shows me that. Just give me 1 second. No, I don't have it here.
What image are you looking for, Rick?
I'm looking for an image with has showing the caliper, the red caliper.
Tariq, I have
Yes.
an image. I have some image want to show you, and please tell us why is it. Okay.
Yes, go ahead.
Okay.
I'm going to stop sharing my screen.
Wait a
Now
second.
you can share your screen now.
Wait a second. Okay, fine. Can you see my screen?
I can.
Yes. So, we met some cases. Just look like this.
Yes.
Condition. Yeah.
Now, what do you think? I'm not going to answer you straight away, but what do you think that eye looks like that?
Oh,
What do you think happened? What do you think happened
oh,
to have that
we
image?
don't know. We don't know what's the problem. What's wrong with it? We try to admit just did it, but just like focus the red line on the cornea. But if we focus on the cornea, and we can't see other part, so it can work, but can't work well.
Okay. Well, imagine if you open your eyes and I take a picture of your eyes, I will get a round picture if I see all the cornea. Now, if you squint, I'm going to have that. That is the difference between having the image like this or having the image like that. This, what you're seeing there is just the area of the cornea, of the epithelium that you could see, because everything else in white is behind the eyelids.
Yes, but
So
we don't think any good. Yes, we don't close the patient didn't close the eye. The eyelid won't be the key. Yes.
I know. So we need to we need to find a way to be able to open the eye of the patient.
Yes.
So what, and I'll show you, give me 1 second.
So Rick, you think the patient just partially opened the eyelid,
Yes.
you know?
Yeah,
No,
absolutely.
the patient just opened their eye.
So what the doctor
Um,
said that the patient did open the the eyelid completely open. And I don't know. We couldn't see it, right? We don't have image to
I-
show the
I would
patient completely open the eyelid.
I would respectfully challenge that.
Okay.
So if you grab a piece of tape, okay, and then you fold the end of the tape, okay, so you can grab it here without getting your eyes, your fingers sticky tape. You're going to, sorry, let me see if I can show you a trick. You're going to put the tape just above the eyelashes. Let me see if I can do this. Okay, you're going to these
Wow,
and
that's
stick
a
it.
strong tape.
Yes.
So if I try to blink, I can't blink because it's all hole there. And when you put the eye seal here on the bottom, you're going to approach with the eye seal, and then you're going to ask the patient to raise. And now it doesn't matter what's your eye physiognomy is going to be open. So this but that's the best way to do it. So you don't tape the eyelashes, you tape on top of the eyelashes, and then you pull it off.
Hi, Rick. I think there is another possibility that we need maybe 6 to 8 scan to generate a 360-degree image. Maybe for this patient, we only did some 1 or 2 directions. So
That could be.
I
That
think
could be.
that's another possibility. Yeah.
Here, and I will
Oh.
also show you something. Here, I'm on a screen. I'll share my screen. Okay. So here on the left-hand side, we can see up here, the red line is the meridian of the scan. No lids in the way. And then as I move down to this one, here you can see the lower lid in the way down here. And that's why you're not seeing a full image up here, right? This is the cornea. The corrected view would be similar to what you would see with an OCT. And again, over here on the left side, you've got some lid in the way. The next image, same thing, more lid. When I go to the map, now I come up to the top. You see how it's blocked out right here? That's because that lid was in the way down there. Okay? And so it could be you only took a few scans. If you look on the lower left down here, it says display meridians. Can you see that? And then I click that box. There's each of the meridians I took. Okay? For this patient, all those meridians cross perfectly in the middle. They fixated well. Sometimes the patient's eye is moving around and they can't fixate well. And so we cannot interpret the data between the scans very well, and you'll get a blank spot as well. But in this case, it was simply that lower lid of that patient. So if I come back over here, you can see that lid is right in the way.
Yeah.
You see? Now, the patients also cut their heads turned in such a way that they're not looking straight ahead. They're looking kind of off to the side, close to the off to the side over here. And so Rick has a good idea to tape some lids. We are working on our speculum that has adhesive on it. We don't have that together just yet, but it works. I've tried it. It works very well. That'll be useful for you, very useful for you. And Andy and the team are working to make that quicker. But that's what we're usually seeing on those scans. Now, when you take the scans of a patient here, you can grab these, see where the blue is? I can move it, and then I can move the whole group so that I'm hopefully getting just the cornea that I really want to see. But now you won't have any image of the cornea up here. But you can kind of try to move it around a little bit to get, you know, the scans you really want to get, okay? So it's just a couple tips. I'm sure in future training sessions, we'll begin to start optimizing scans, what we need to do there, okay? I wanted to at least show that.
Now, do they have, do you have, Sabrina, William, do you have a computer that have that software?
Yes. You have a
They have-
laptop with our software on it, yes.
Yeah.
Okay, so next time you have that case, you need to export the patient, and then you can play with that patient in your computer, and you can see what went wrong.
Mm.
Okay.
Can I, want me to show you how to do that real quick?
Yes,
Uh,
please.
Okay, it's right here. From the patient screen, let me share. From the patient screen, you just highlight the patient name and you right click. You can export the patient. If you use export anonymously, the patient name is not on there. Okay, there's no data about the patient name. But you, by exporting that, you export and you just move it to a jump drive or wherever you wish to move that image, and that whole file will come over. And then when you get that jump drive or what have you, then you're going to come here and you're going to right click and import a patient. And then surf and look for your jump drive and then pull that patient file in. And then you can look at it in your software.
So, Barry, by doing this, we will be able to say when they do the measurement, and we will be able to see the how the eye open, you know, how the
Yes.
eyelid open, something like that.
Yes.
You can see everything.
You can see
Oh.
everything. And there's information within the ScanSet file. We can tell exactly how the computer worked, what the settings were. We can tell everything about it. But this will give you the full, as if you were there at the instrument, take all the measurements. Yes. Okay, so
And
I'm going to
being
send you an
able-
email on how to do that, okay?
I thought when the technician or doctor, I don't know who will operate the machine, when they do this imaging, they should tell the patients, you know, they can see the eyelid open, right?
Oh,
See
yes.
yeah, they should tell the patients, okay, complete open eye, and to complete expose your cornea to the transducer, I think.
But they may not be looking at the lines where the scans are. So they might be looking at the eye because it looks, that eye looks open. But when you see the lines, the lines are covered completely by the eyelids.
Yeah.
Mm.
And that is a problem. So it's not a problem of having the eye open or not. It's a problem to, is the area that I'm scanning is showing in the image, because I can do scanning that eye to measure ICLs. I will shrink the lines. I will put them all together between hours 3 and 9, and I will be able to provide measurements. But if I'm analyzing, you see, if I do that, I can.
Oh, you can do that part of the. Okay.
Yes. So you can
Okay, got it.
adapt the measurement based on the area that you want to scan. But if you want to do an epithelial mapping, it will defeat the purpose, because usually, and I say usually because I had a case of an atypical keratoconus last week. Usually the keratoconus is on the lower side,
Mm.
and if you measure, if you do what Barry did, that had it, you know, side to side like a bow tie, you don't measure the top and the bottom. You cannot use that for keratoconus, but you can for ICLs. An image like that, a little bit higher, but an image like that will perfectly fine go fine for an ICL. You see, an image like that, it will be perfectly for an ICL.
Yeah, because
Absolutely
you're
perfect for
measuring
an
right in
ICL.
here. You're seeing it all.
But it
Okay.
will be rubbish. It will be absolutely rubbish for an epithelial mapping, because the only thing you're going to see will be that.
Okay.
Okay, we'll try it. And we will use the tip to open the eyelid and try.
And if
then
if you have a patient like that, a problem like that, you can send us the patient file.
yeah,
Please send the patient.
We have provided the file to Matt.
Okay. So you export the patient already?
Yes.
Or just the images.
Let me check. 张俊，你发给的只有图片，还是说那个病人的所有的信息？
我发他的是 Meta 上下载了一个那个扫描的集锦，里边有所有的数据吧。
It covers all the data.
So he got the log files, everything.
Yes, everything. Okay. Thank you.
Okay, perfect.
Yes, appropriate training. Thank you, Rick.
No, my pleasure. Are there any other questions from the team? You want to ask them if you have any other question?
Thank you, Rick. This is Daniel, and I think it's a good help for us to know better about ultrasound and oxygen after your training. And I have one question: is that I was impressed by one of the previous slides that the coverage of the scan orbit can be adjusted by two orbit. Maybe one is arc and the other one is linear. So is this a fact we have already achieved inside 100?
Well, I'll tell you something even worse. Okay. So give me 1 second. Let me modify. Give me 1 second. I'm going to show you something. I'm trying to. Okay, I have it here. Okay, there you go. I'm modifying this so I can show you what I mean. And just bear with me, because I'm trying to do something a little bit different here. Okay, I'm going to share my screen and explain it to you in a second. Can you see my screen here?
Actually, no.
No, you cannot, because I haven't pressed share. Okay. On the linear scan, which is the second best option, the scan moves on a linear way, but this is not the typical UBM scan. A typical UBM scan will work like that. It's lines that they are going all from one place. So they're going to go one line, then it's going to move in this direction all the time. What happens is that if you have these same lines in an anterior segment image, if you have these lines in an anterior segment image, you will never be truly perpendicular to the anterior segment. The difference is with the R scan, difference much better than the linear and the conventional UBM is that we move in the same arc parallel to the cornea, or as parallel as we can from the cornea. And that is the difference. So this is, you will always be perpendicular to the area where here cannot be perpendicular. You only will be perpendicular here if you are in axial, nothing else. Okay.
Yeah, I know. My question is, do we have both arc orbit or both arc orbit and the linear orbit? So because you know different patients have different coverage, can we adjust the coverage among different patients?
No, because our probe, it's based on, it moves on a car that is already arced.
Rick,
We could
I'm going to
we could
correct
do,
you. Rick,
you know,
if I can correct you, please.
but I was about to go there.
Okay.
We have the ability to move the back of the plate in different positions. So
Okay.
the probe, generally speaking, will move in an arc. If we want to move the probe in an axis, like, you know, up and down or vertical, we have the ability to do that. So
Okay,
we
I
don't.
see.
So there are like 3 different levels of movement in the base plate on inside of the unit. You have one big unit that turns around, and it's like I don't know if you can see my hands, but it does that. There is another movement that is in block, and it moves like that, and then there is another movement that goes like that, which is the probe. So you have those 3 movements happening at the same time. We can replicate the linear scan, yes, and we can do the R scan, yes. What we cannot do is what a regular ultrasound does, that is just moving that way, because we don't want to do that. There is no benefit to it.
Okay, I
Is
see.
that okay,
Thank you.
Barry?
Yeah,
It's,
so a little bit simpler. So as the probe is moving on the arc, the whole plate that the arc rides on moves side to side. So you get this oval shape too. We
Okay.
can actually, as instead of an arc this way, we can do one that goes that way. So we're getting the back of the capsule. We're moving in 5 axes.
okay.
Axis. Okay, thank you.
Any
Another
other question?
Nope.
Okay.
It's
Rick,
everything.
can you share? Rick, can you share me the another slides which you shared today?
The new slides, yes, I can.
Okay, thank you.
Yeah. No problems.
Okay, so Rick, I did record this. It's been recording this training. And when you're done with presenting, you will see in the comment box, Rick, on your screen, you're going to see a link, and others will be able to get that link and look at the recording. That's I hope so. I'm not sure with how it transmits, whether it's through Google or through its WeChat. I'm not sure, but we have recorded this.
We have recorded this too.
Oh, good. Very good.
There.
Fantastic. Thank you.
I see that.
Okay.
Yeah.
And one more question is that maybe Rick, you can share with us some patients' data with us. We can practice them in our own computer, our own machine. Maybe it helps us to get familiar soon.
You don't have any patients on your computer?
You do.
Maybe a few, just a few. For we didn't if we put this machine in hospital, we need to get the authorization from doctors before we can use the data. So in our own company, the data was very few for us.
So Sabrina, when I first did the training with you guys, remember we loaded a whole bunch of images
Yes.
on your system. So you should have quite a few images there already.
Okay.
Just
Okay.
practice ones.
Yeah. Yes. Daniel, but we have maybe a couple patients. Let me check. 张俊，我们那里面有多少的那个病人的信息啊？有多少病人的大概？张俊，
就咱们那个机器上，还是那个之前在那个公用电脑上，咱那个机器上大概有咱公司的，基本上都是有7、8个吧。
公共电脑上的呢？
公用电脑上大概也就是个10个左右吧，之前考的。但是他之前考的有一部分资料是不能用的，有一部分病人信息是打开不了的。
Okay, Barry.
Yes.
You know, we have around 10 patients' data in the computers because you provide some data, but we can't open it. So, if how many patients' data do you have total? How many?
So,
How many you have patients?
how many do we have, or do you have?
Yes, I think Daniel, do you want to get some typical data? Yes, that we can practice. Yes, Daniel.
Yeah. One purpose is for get familiar. The other one is for us to get some marketing promotion with typical images. It will get easier for us.
So we need to put together a file,
Yeah.
and send it via WeChat of multiple patients and multiple images for marketing.
Yeah.
Okay,
I can do that.
fine. You can
Yes.
transfer by the.
I will transfer. I will send those to you.
Okay.
And William, maybe you can install the software in your own computer. So maybe you can use it in the following KOL visiting. Yeah.
Got it.
So Barry, would you please send the software setup package to William?
I will reach out to Matt and have Matt do that, okay? Because you have to have a SQL database. It's not just straight software. It's fairly complex. Remember, Matt had to set the computer up the last time, remember?
Yeah. Okay, fine.
So we'll have Matt do that, okay?
Yeah, fine.
Perfect.
Okay. I have no more questions.
There you go. Nothing else then?
We all clear.
Okay, good.
Thank you.
Rick,
Thank you
when is the
again.
next training?
Next training.
Well, I have a personal problem because I'm going to be on holidays for the next 2 weeks.
Okay.
Congrats.
Christmas? No Christmas.
Enjoy your
So
I'm
So-
happy to
so-
do. I'm happy to do one myself. I can do
So-
as much as you wish.
So
Wow.
what we need to do, what we need to show them now is the capabilities of the inside, which I believe is now ultrasound applied to the inside. And that's something that I was working on, Christine, and
Okay.
we can take this one off of the phone. So probably we can do a meeting probably in 2 weeks. We can probably do a meeting in 2 weeks. And then we can organize something in a couple of weeks, so you guys have a presentation of the inside 100 and what sort of how does it work. I want you to understand how does it work, because when you understand how does the inside 100 works, you're going to have a much better understanding the why we're better than any other ultrasound in the market, and that is the idea.
Okay.
Okay.
Cool.
Good.
Excellent. Okay, perfect.
Okay.
So we will send you in. Let's commit to in 3 weeks. We'll send you in 2 weeks. We'll send you in 2 weeks so you can translate it, and then we do the next week, the next training in 3 weeks. Is that okay, or that's too long?
Mm.
Or we can do it in 2 weeks. That's fine. Doesn't matter. So we have all the materials ready.
receive the equipment？我们的那个设备大概什么时候到？
现在上海疫情，应该现在已经在路上了。如果说没有疫情的话，大概4月10号左右，可能也快了。
所以就是如果要是那个时
20
候
号左右。
20号左右。
也差不多2周，然后那这样子的话，
你们这段时间先把软件熟悉了，然后如果有数据的话，我们先把数据自己先操练起来。
可以。
OK。
Okay, fine, Rick. A good
2 weeks.
suggestion.
Okay.
Yes, 2 weeks.
Okay, perfect. Okay.
Okay, folks.
Well,
Thank you.
Thank you,
Tiffany.
Barry. Thank you, Rick.
Thank
you.
you,
Bye.
Rick.
Bye bye.
Have a good day. All right, bye-bye.
bye. No worries.
Bye bye.
Bye.
Bye bye.
Bye. Bye,
Bye.
Jean.